Your body is a museum of evolutionary history. Walking around inside you right now are remnants of your ancient past, body parts that once served crucial functions, but are now essentially useless. Evolutionary leftovers that earlier versions of humans desperately needed, but that you could live without just fine. Evolution doesn't work like an engineer designing a machine from scratch. It's more like endless renovations on an old house. You keep adding new features, but you rarely bother removing the old ones unless they're actively causing problems. If something isn't hurting your survival or reproduction, evolution just leaves it there. The result is that your body is full of vestigial structures, biological artifacts from earlier stages of human evolution. Some are harmless curiosities. Others occasionally cause problems. But all of them tell the story of where we came from. So let's tour the useless parts of your anatomy and explore why evolution left them behind. Reach around and feel the base of your spine. That small triangular bone at the very bottom is your coccyx, commonly called your tailbone. And it's exactly what it sounds like, the last remnant of a tail. Millions of years ago, the primates you descended from had proper tails, long, muscular structures that helped with balance while moving through trees and provided counterweight when climbing. For arboreal primates, a tail was essential equipment. But as early hominids moved to the ground and adopted upright walking, tails became less useful. A tail is great for balance when you're horizontal and moving through branches. It's mostly in the way when you're vertical and walking on two legs. What's left is the coccyx, a small fusion of 3 to 5 vertebrae at the end of your spine. It does anchor some muscles and ligaments in your pelvic floor, but you could absolutely live without it. People who have their coccyx surgically removed due to injury generally adapt just fine. The coccyx is also infamously easy to injure. Fall on your backside hard enough, and you'll fracture your tailbone, which is excruciatingly painful and takes forever to heal. It's a perfect example of a vestigial structure that occasionally causes problems, but serves no critical function. Interestingly, human embryos actually develop tails during early development. Around 4 to 5 weeks after conception, the developing embryo has a visible tail, but by 8 weeks, this tail is almost completely reabsorbed. Very rarely, a baby is born with a vestigial tail that can be surgically removed without issue. Most people develop 32 teeth over their lifetime, including 4 third molars that typically emerge in late adolescence or early adulthood. These are commonly called wisdom teeth. But for many people, wisdom teeth cause problems. They often become impacted, meaning they get stuck and can't fully emerge. They crash into neighboring teeth, grow at weird angles, cause pain and infection, and frequently require surgical extraction. So why do we have them? In the deep past of your species, humans had significantly larger jaws and tougher diets. They ate uncooked meat, fibrous plants, roots, and other foods that require serious grinding power. Having extra molars was genuinely useful for processing this rough diet. But as humans developed cooking, agriculture, and food processing, diets became softer. Evolution no longer favored massive jaws and extra grinding teeth. Over thousands of generations, human jaws gradually became smaller, but teeth didn't shrink at the same rate. The result is a geometric mismatch. We still develop the same number of teeth that early humans had, but we're trying to fit them into smaller jaws. The wisdom teeth, being the last to emerge, often simply run out of room. Interestingly, evolution appears to be slowly solving this problem. Some people never develop wisdom teeth at all. Studies suggest that around 35% of people are missing at least one wisdom tooth. Evolution is gradually phasing them out, but it's a slow process that takes thousands of generations. Compared to most mammals, humans are remarkably hairless. We have roughly the same number of hair follicles as chimpanzees, but most of our body hair is so fine and light that it's barely visible. Earlier in human evolution, body hair was much thicker. It served as insulation, trapping a layer of warm air close to the skin. In cold environments, thick body hair was genuinely useful for maintaining body temperature. But as humans developed clothing, shelter, and eventually climate control, body hair became less necessary. We created artificial insulation that worked better than fur, and in many environments, less body hair was actually advantageous because it improved cooling through sweating. Humans are exceptional sweaters. We have more sweat glands than almost any other mammal, and we can cool ourselves very efficiently through evaporative cooling. But this system works much better without thick fur trapping heat. Less body hair means better temperature regulation. So over tens of thousands of years, humans became progressively less hairy, and this trend appears to be continuing. Scientists predict that humans will likely become even less hairy over time, though the process is extremely slow. Body hair persists in a few areas where it still serves functions. Hair on your head protects your scalp from sun damage. Eyelashes and eyebrows keep debris and sweat out of your eyes. Underarm and pubic hair may help with scent distribution. But the fine fuzz covering most of your body, that's just evolutionary inertia. It's not hurting anything, so evolution hasn't bothered removing it completely. Hold your arm out, palm up, and press your thumb and pinky together while flexing your wrist slightly. Look at the inside of your wrist. Do you see a thin tendon standing out in the middle of your forearm? If you do, you have the palmaris longus muscle. If you don't see anything, you're among the 10 to 15% of people who are missing this muscle in one or both arms, and you're functioning just fine without it. The palmaris longus is a slender muscle that runs from the elbow to the palm. It's one of the weakest muscles in the forearm and contributes almost nothing to grip strength or wrist function. People missing it show no measurable deficit in hand function. So why do most people have it? Because tree-dwelling primates needed it. Species that spend significant time in trees need strong, flexible grips for swinging from branches. The palmaris longus contributed to this grip strength. But as humans moved to the ground and developed tools, the specific gripping mechanics used for brachiating through trees became less important. The palmaris longus became redundant. Evolution is slowly removing it. The fact that 10 to 15% of people lack it entirely, with no negative effects, suggests it's on its way out. Interestingly, the palmaris longus is sometimes used in reconstructive surgery. Because it's expandable, surgeons can harvest it as tendon graft for repairing damaged tendons elsewhere in the body. You're cold, or you're watching a scary movie, or you hear a piece of music that moves you, and suddenly, the hair on your arm stands up and your skin gets bumpy. Goosebumps. This reflex is triggered by tiny muscles called erector pili muscles attached to each hair follicle. When these muscles contract, they pull the hair upright and create the characteristic bumpy appearance. When your species was still covered in thick fur, this reflex served two purposes. When cold, raising the body hair would trap more air close to the skin, creating better insulation. When threatened, making the hair stand up would make you appear larger and more intimidating. You can see this reflex working effectively in other animals. A cat facing a threat puffs up its fur to look bigger. A dog in cold weather fluffs its coat for warmth. But in nearly hairless modern humans, goosebumps accomplish absolutely nothing. Raising fine vellus hairs doesn't create meaningful insulation, and making your arm hair stand up doesn't make you look more intimidating. Yet, the reflex persists because the neural wiring is still there, and it's not causing any problems. Your sympathetic nervous system still triggers the erector pili muscles in response to cold or emotional stimuli. The muscles contract, the hairs stand up, and nothing useful happens. Goosebumps are a perfect example of evolutionary momentum. The hardware is still installed and still runs the old program, even though the output is now meaningless. Here's a question. Why do men have nipples? They serve no function. Men don't breastfeed. Male nipples don't do anything. The answer is developmental efficiency. All human embryos start with the same basic blueprint. In the first several weeks of development, embryos follow a default pathway that includes developing nipples and mammary tissue. Sex determination happens when the Y chromosome triggers the development of testes, which then produce hormones that masculinize the developing body. By the time this process starts, nipples have already formed. Evolution never bothered creating a mechanism to remove them in males because they're harmless. This is a common pattern in evolution. If a structure isn't actively harmful, there's no selective pressure to remove it. Male nipples don't hurt survival or reproduction, so evolution just leaves them there. They're not entirely without function. Male nipples have the same nerve endings as female nipples and can be sensitive to touch. And very rarely, men can develop breast tissue and even produce milk under certain hormonal conditions. But for the vast majority of men, nipples are purely decorative. Male nipples are evolution's way of saying, this costs nothing to build. It's not hurting anything, so why bother removing it? Your body is full of these evolutionary leftovers, structures that once mattered, but now persist simply because they're not causing enough problems for evolution to bother removing them. Some vestigial structures are completely harmless curiosities. Others occasionally cause medical issues. A few might still serve minor functions we haven't fully understood. But all of them tell the story of your evolutionary history. They're evidence of where you came from, what challenges earlier humans faced, and how your body adapted over millions of years. You're not a perfectly designed machine. You're a heavily renovated body, carrying remnants of previous versions that serve different purposes in different environments. Your body is a living archive of evolutionary history. Every useless part tells a story.